Hello students, welcome back to our class. We were dealing with the lesson phenols. This is a part of alcohol, phenols and ethers lesson, right? So we were dealing with this topic and now we will move ahead with some other important characteristics of this topic, phenol. So we have already covered the preparation methods of phenol and general introduction. Now we are going to discuss the properties, and in terms of property, the most important property which you will tend to know is about acidic strength. These phenols are capable of showing acidic strength. This acidic strength is directly proportional to you have learnt about effects, right? So acidic strength of phenol will be more if a compound is showing -I or -M effect both, and it will decrease if these factors will decrease. And it is inversely proportional to +I or +M effect. What are -I, -M, +I, +M? Inductive effect and mesomeric effect we are talking about here. Okay, so directly to -I and -M and inversely to plus. So that means if these effects are increasing, acidic strength will decrease, and if they are decreasing, acidic strength will increase. So why do we call this phenol acidic? Because this phenol has this structure, right? It has two lone pairs present on oxygen atom, which will cause what? Which will give oxygen higher electronegativity than hydrogen. So it will have the tendency to attract the electrons towards itself, and it will result in the release of this proton as H plus. Okay, and the structure that is left will be known as your phenoxide ion. So any substance that is capable of giving H plus ions is known as acid, and here the anion that is formed in this example is known as your phenoxide ion. Both phenol and phenoxide ion is capable of undergoing resonance. Due to which release of proton becomes, or it facilitates an easy removal of proton both. Okay, so in both the examples, so due to which they show acidic strength. So if we take three examples like orthonitrophenol, metanitrophenol, and paranitrophenol. These three examples. Okay, let's label them. This is 1, this is 2, and this is 3. These ortho, meta and para are capable of showing what? We will see whether they are showing both -I and -M, or only this +I +M, or only -I or only -M, right? We will have to check that. So you have learned about this in earlier classes as well, in earlier topics as well, that orthonitrophenol and paranitrophenol both are capable of showing your -I and -M. I will quickly recall that. Okay, why we are saying this? because nitro group is attached on phenol, right? And this nitro group has nature electron withdrawing. This is EWG group, electron withdrawing group, right? So any group that is capable of withdrawing electrons from the ring, that means it will take the electrons, then ring will take the electrons from oxygen, or definitely, and this oxygen will ultimately extract electrons from proton, this H. So this will facilitate the release of proton more easy, and that is why it is known as minus I and minus M both. And minus M, why? Because they will, electrons will be capable of undergoing resonance, mesomeric effect. So this para and ortho both are capable of showing this effect. But this metanitrophenol, because we know OH is orthopara director, we will see how, okay, we will show you the resonance as well. So what happens during resonance, delocalization of pi electrons, this OH group is actually increasing the electron density on ortho and para position, but here we have meta, right? So electron density is not present here. Minus M effect. So if you label them as 1, 2 and 3, and now I ask what will be the decreasing order of acidic strength between orthonitrophenol, metanitrophenol and paranitrophenol. So what will be your answer? And remember this part as well, that acidic strength is seen in terms of OH group, okay, always. So here, as I said, this meta is able to show resonance, but it does not increase the electron density. So this NO2 group has no role in increasing electron density or taking the electrons away from the ring, right? It will take, but it will not increase, or electron density has no part in this example. So this will be our least acidic example. So I will put this 2 in the last, okay. And now if you will compare 1 and 3, so it is said that 3 is more acidic than 1. This is the acidic strength order, that paranitrophenol is more acidic than orthonitrophenol, and orthonitrophenol is more acidic than your metanitrophenol. Why? Because in orthonitrophenol what happens, that it is capable of showing hydrogen bonding. Intramolecular hydrogen bonding is possible between the H and O atom of the same molecule. It shows intramolecular hydrogen bonding. So when it shows intramolecular hydrogen bonding, then the association is present within the same molecule. So their boiling point also decreases. When boiling point decreases, that means volatile nature increases. So we'll call it volatility, that increases. And these ortho and para can be separated by steam distillation. This we know this very well. So obviously if they are associated, right, within the same molecule, so this H is not available for release. So their acidic strength will decrease definitely, but it is more than this meta. But in para, the intermolecular hydrogen bonding exists. 2 molecules are needed. So they exist in associated form. 2 molecules are more than the 1 molecule, right? So their boiling point will increase, volatile nature decrease. So all these things happen when you compare the acidic strength of ortho, meta and paranitrophenol, and the order is 3, 1, 2. Okay. So this was about acidic strength of phenols. So now on the screen you can see we have 2 questions given to you, and these questions are being asked on the topic acidic strength only. So we were discussing that. So let's quickly see whether you are able to apply the knowledge or not. So here we have been given this bond line notation of an aliphatic alcohol, okay, and then you have been given 2,4,6 trinitrophenol, and then in the C we have been given metanitrophenol. So if I ask you now that what will be the acidic strength order, that is increasing order, okay, or let's say decreasing order, okay. So let's make its decreasing order. So what will you do? You will first compare these three examples and we will check that which one will have the highest acidic strength. So let's first focus on that. So on comparing, you have seen we have one aliphatic alcohol and two phenols, that is aromatic alcohols, are given to us. So when you compare alcohol and phenols, so we have discussed that phenols are always more acidic than alcohols. Why? Because they are capable of undergoing resonance, delocalization of pi electrons takes place. So the lone pair electrons present on the oxygen, it takes part in resonance. So it is not available. So that oxygen then turns towards hydrogen and extracts the electrons towards itself. So that's how it facilitates the release of H plus ions. So that is why it is more acidic than alcohol. Alcohol has no such example. Alcohol does not show such trend because alcohols, this is one general alcohol, right? And this is your phenol. So phenol is capable of extracting electrons, as we said, but this R part attached to the OH is an electron releasing part and it will give electrons to O. So release of H will not be easy. So that is why acidic strength of alcohols is always less than this phenol. And why it has more, that I have just explained, because of the resonance. So the least acidic will be this A, right? So if we are making an decreasing order, so we will always put this A in the last, and this B will come first and then this C will come. So this is our order of decreasing acidic strength, that B is most acidic. Why? Because it will show minus I and minus M effect, whereas this metanitrophenol will only show you minus M effect. We are seeing this in terms of OH only, okay. So that is why B is more, and then this C, because it is aromatic, that is why C, and last one is A. So this is your decreasing strength of this question. Now we will move on to this question. Again, three examples are given to us and you have to make the acidic strength order. We will make the decreasing acidic strength order only. So here obviously the most acidic will be this 3,5-dinitrophenol, because it will show you minus I and minus M both, right? And this is phenol. It will not show any effect because it has no group attached to it. So it will show its simple resonance effect, right? And here it will, so we'll write minus M effect is possible. But in terms of this paramethylphenol, it is capable of showing plus I and plus M effect, because CH3 is an electron releasing group. So it will decrease the acidic strength. It will give electrons to the ring. So ring will take the electrons from this side, methyl side. So O will not be able to extract electrons because O is already getting electrons. So that is why the most acidic one is A. A will be having more strength than B, because at least it is capable of showing minus M, no? And C will be the last. So this is acidic strength order in this given example. So that's how we will solve for given examples. So after acidic strength topic, we will discuss about the consequence or effect of acidification, that because this phenol is capable of showing acidic nature, it shows esterification reaction as well. It will react with the acids. So let's take an example of benzoic acid only. Okay, you can take an aliphatic acid as well. We will show you the both reactions. And take phenol. So what happens that bond breaks from this side and COOH bond breaks from this side. So this OH and H combines to form H2O. Okay, and rest part is your ester. I'm making this ring at this side. Okay, so this is the structure C6H5 COO C6H5 in this given example. Okay, and this reaction happens in the presence of concentrated H2SO4. This is esterification, and ester is formed in this given example. You can show the same reaction using an aliphatic acid as well. So when an aliphatic acid like CH3COOH is reacting with the phenol, in the presence of concentrated sulfuric acid only. So what will happen? Bond will break from this side, these will combine together to give you water and an ester molecule. Phenyl acetate or phenyl ethanoate, that will be its example, and a molecule of water is removed. So this is esterification reaction. Now we'll move on to next part in this session, that is aspirin formation. So phenols are capable of showing formation of this important medical compound aspirin, which is an analgesic, right? So this is prepared by using modification of a product that is being formed in Kolbe's reaction. You have learned Kolbe's reaction. We will see again Kolbe reaction. Don't worry about that. So let's first see the Kolbe reaction. So in Kolbe reaction, what happens? This phenol first reacts with it will convert it into its phenoxide form. Okay, and then it reacts with carbon dioxide, and subsequent acidic hydrolysis is done. Then it gets converted into orthohydroxybenzoic acid, which is known as your salicylic acid. This aspirin is known as your 2-acetyl benzoic acid. Okay, it is a modification of this compound, this aspirin. So what happens that when this salicylic acid now, when reacts with the acetic anhydride, okay, then it gets converted into an acetyl group is introduced on O part of the OH group, okay, and CH3 COOH is released. A molecule of ethanoic acid is removed. So this is your aspirin, which happens through coal-base reaction. So it proceeds first till here, you will write it coal-base reaction, okay, and then this modification is for aspirin formation, okay. So after that we'll move on to next, electrophilic aromatic substitution. So these phenols are capable of showing electrophilic aromatic substitution reaction. Where an electrophile will be introduced then? It takes place or gets added up on the ortho and para positions of phenol structure. So that happens because electron density is more at that time because of resonance on phenol. So I will show you the electrophilic substitution reaction in phenols, and before that I'll show you the resonance in phenoxide ion, that why the electron density considered more at ortho-para positions. So this electron lone pair first comes down from oxygen side to form the double bond, and this bond pair electrons moves on the adjacent next carbon to form the lone pair of electron. So due to which a double bond is introduced here, and this bond pair will come up on the carbon as this lone pair. Then in the next step, this lone pair will form the bond pair, and this bond pair electrons will move on to next carbon as lone pair. So this bond pair is this, and lone pair is shown in this manner. Then again this lone pair will move to form bond pair, and this bond pair will move on this carbon to form the lone pair of electron like this, in this manner. And then in the next step, this lone pair will form bond pair, and this bond pair will move on to form its lone pair of electron. In this manner. So from here you can see that electron density is rich at which position? This second position, and this fourth position, and then again this sixth position, right? So this is known as your ortho and para positions, and that is why the incoming electrophile comes and adapts at this position. So this is resonance in phenoxide ion, and in the same manner you can show the resonance in the phenol molecule as well. Instead of this minus you will see H there, okay, and rest case is same. So now we'll talk about some of the electrophilic aromatic substitution reactions, in which the very first example is nitration. So this nitration actually happens, it is an electrophilic substitution reaction. So the electrophile is NO2 plus, do remember this, okay, and the nitrating reagent is concentrated HNO3 and in the presence of concentrated H2SO4. But if you use dilute HNO3, then there is different product, okay. So I'll write here different case. So we'll see when dilute is used and when concentrated is used, so how products are changed. This is phenol, and when it reacts with dilute HNO3 in the presence of concentrated H2SO4. So what happens that the concentration of the electrophile, that is NO2 plus, will be less, right? And then it results in the formation of ortho and para products. Ortho para products are formed in different concentrations when dilute HNO3 is used. So ortho product is known as orthonitrophenol and para product is known as paranitrophenol. Paranitrophenol concentration is generally more than this orthonitrophenol, and that is why it is the major product and the minor product is orthonitrophenol. So this is the reaction with dilute HNO3, A, okay. Now let's see B reaction when concentrated HNO3 is used. So when you use reagent will be same, but their concentration is increased now. So it will result in the formation of a whole orthopara substituted phenol product, which is known as 2,4,6-trinitrophenol. And it is also known as picric acid. It is not considered as an acid like carboxylic acids, okay. The term here acid, that when you are comparing it with the carboxylic acids, but it is not a typical acid, okay. So in this manner the reactions are shown when dilute HNO3 and concentrated HNO3 are used. After that we'll see next electrophilic aromatic substitution reaction, bromination. Here also two different cases are possible. Let's see those cases. So when phenol reacts with bromine in the presence of a solvent carbon disulfide, okay. And second case is when this phenol reacts with aqueous solution of bromine, okay. In aqueous solution of bromine, this bromine concentration is more and it will give you the electrophile bromoniumine, like chloroniumine. So bromoniumine is there, Br plus. So when bromine is dissolved in carbon disulfide solution, it results in the formation of ortho and para product, in which para product is always the major product. This we know this very well, right? So orthobromophenol, para-bromophenol, and when aqueous solution of bromine is used, you can see that excess of bromines are there, right? So it will result in whole substitution at the same time in the molecule. So it will result in the formation of 2,4,6-tribromophenol. Para 1 is the major one. So this is the two cases when you use different solvents, okay, in case of bromination. Rest other electrophilic aromatic substitution reactions like sulfonation, Friedel-Crafts alkylation and acylation have no exceptional thing. It is same as you have learned in your benzene topic. So instead of benzene, only phenol is there and it is ortho-para directed. So incoming electrophile is going to attach on respective ortho and para positions. Para will be the major product. So I am showing the two important cases here in case of this electrophilic aromatic substitution reactions. So with this we will wind up our part 2 of topic phenol. Then we will meet again with part 3 where some other important reactions will discuss from this topic. Till then, revise these reactions. These are important ones, and in terms of competitive exams, questions are being asked from these all reactions. Thank you so much.